Hello students, this is the second part of lecture 21. In the first part we discussed three types of change of variables. One was for R2 which was polar coordinates and other two were for R3 which were cylindrical coordinates and spherical coordinates, right? And today we are going to talk about general change of variables for which we need this concept of Jacobian determinant. So let us look at the definition. If x and y are functions of u and v, then their Jacobian determinant is the determinant of the derivative matrix. So this is a notation that one uses for this Jacobian matrix determinant, which is del or partial x comma y, so and partial y, u comma v. So in the numerator you put the variables which you want to differentiate, okay, which are functions of the variables that appear in the bottom. So x is a function of u and v and y is a function of u and v. So you can talk about the derivative of x with respect to u, x with respect to v, y with respect to u, y with respect to v. So you take the determinant of this matrix. Okay. And if you have three variables x, y and z which are functions of u, v and w, then this derivative matrix is actually a 3 by 3 matrix, as you know, and the determinant of that matrix is called Jacobian determinant. Okay, and the notation is quite similar to what we had for two variables. You have on the numerator you have variables which are functions of the other variables which appear in the bottom. So if you look at the first row, x, it's the derivative of x with respect to UVW. Second row is derivative of y with respect to UVW. And third row is derivative of z with respect to UV and W. So let us look at what was happening for polar coordinates. So for polar coordinates, x and y were functions of r and theta, right? So if you look at the Jacobian determinant, then in the first row you will, so there are two variables, right? R and theta in place of u and v. So you get xr, x theta, which is derivative of x with respect to r and derivative of x with respect to theta, and similarly y with respect to r, y with respect to theta. So if you compute these derivatives, you compute the determinant, you get r. Okay. Now let us look at cylindrical coordinates. There x, y and z, you had three variables and they were functions of three other variables r, theta and z, right? So if you compute the determinant of this matrix, you compute what these partial derivatives are and you get r. Okay. So in the case of polar and cylindrical coordinates, both you are getting r as this Jacobian determinant. Now let us look at spherical coordinates. In spherical coordinates, you have to do a little bit of more computations, but the determinant comes out to be rho square sine phi. Okay. So now you are already aware of these terms, right? So the Jacobian determinant terms are in the case of polar and cylindrical coordinates, and rho square sine phi in the case of spherical coordinates appeared as an extra factor in the change of variables formula, right? And the question is this a coincidence or is that the case all the time? Now the answer is that it is not a coincidence. That is what happens all the time. So let us look at the general change of variables formula. So let x and y are functions of u and v and let D be a region in the xy plane and D star be the corresponding region in the uv plane. Okay. Then if you compute the double integral of f over the region D in xy coordinates, that's same as you replace x as a function of u and v and replace y as a function of u and v. You have an extra factor which is the Jacobian determinant du dv and over D star which is the corresponding region in the uv plane. Okay. So now it's clear, right? If you convert into polar coordinates, then it perfectly fits with what we have already studied, because this determinant is r, right? And here notice that we are putting a modulus here. Okay, so you multiply by the absolute value of the determinant. So in the previous slides, in the case of polar, spherical, cylindrical, they were all non-negative numbers. So there was no need of an absolute sign. But in general, you have an absolute sign. Okay. And in the above, x and y are C1 functions of u and v, because we want to make sense of this, except possibly on the points of boundary. Each point of d star corresponds to just one point of d and vice versa. So in some sense, the change of variables is invertible, except on the boundary where they could be, it may not be injective, but inside the region, it has to be a one-to-one map. Now similarly, if x, y, z are functions of u, v and w is a region in x, y, z space and w star is the corresponding region in the u, v, w space, then you have a similar formula for triple integrals. You multiply by the Jacobian determinant and absolute of that. Okay. And similarly, a similar note, this x, y and z are C1 functions of u, v, w, and except on possibly on the boundary, you have a 1-1 relationship. So now there is, you might wonder why we are multiplying it by this, because the idea, I'm not going to go into the proof, but geometrically what happens is, let's say in the case of R2, you take an infinitesimal rectangle and you see what happens to that when you convert it into the new coordinates. What happens is the area gets transformed to this quantity, absolute of the Jacobian determinant times du dv. So that's the area of the new region that you get when you transform an infinitesimal rectangle in xy plane of sides dx and dy. So this is the extra factor. Similarly, in the case of R3, an infinitesimal box of sides dx, dy, dz goes to a region in R3 whose volume is given by absolute of Jacobian determinant times du, dv, dw. Okay. So now things make sense, right? Whatever we were doing for polar, spherical or cylindrical, they fit in these definitions. Let us look at a few examples. So the first one is, let D be this rectangle 0, 1 cross 1, 2, and let x be equal to 4u and y is 2u plus 3v. So x and y are functions of u and v. Find the region D star in uv plane corresponding to D. That's the first question. Use the variables u and v to integrate this double integral. So first of all, D is a rectangle, right? So it's very easy to compute this integral directly by putting in the limits, right? You know how to do it. But we are going to use what is asked in the question. So now x lies between 0 and 1 and y lies between 1 and 2. So you substitute what x and y are from the new variables from these equations. So this is what you get, right? X is 4u and y is 2u plus 3v. So if you expand these, if you rewrite these inequalities, the first inequality becomes u lies between 0 and 1 by 4 by dividing this entire inequality by 4. And the second one, now u is independent of y. The limits of u are independent of v, right? So v limits can be obtained as functions of u, right? So you first subtract the entire inequality by 2u and divide by 3. So this is what you get. So if we plot the region D, it's just a rectangle, right, in xy plane, which is 0, 1 cross 1, 2, this shaded region. Now when you take it to UV plane, your V lies between this and this, right? Now how do you draw inequalities? You look at the equalities on either sides. Okay, so you look at V equal to 1 minus 2u by 3 and V equal to 2 minus 2u by 3. So this gives you these two lines. Okay, now u lies between 0 and 1 by 4, which is 0 to 1 by 4, and then you are going from this line to this line, right? So D star is this shaded region. Okay, so take a pause and convince yourself that this is really D star that you get here. So what happens is this rectangle gets transformed into this parallelogram in UV plane. So now for integration purposes we need Jacobian determinant, which comes out to be in this case 12. Okay, so if you look at the double integral, you get the double integral over the new region D star x minus y by looking at this expression becomes 4u minus 2u minus 3v, which is 2u minus 3v, times the absolute of the Jacobian determinant du dv. Now absolute of Jacobian determinant is 12, which is a constant. I have taken it out. You have 2u minus 3v. Now u limits are constant limits, so it has to be outside. And V limits are in terms of u, so they have to be inside. This is very crucial. You have to understand this. If a variable has limits which is in terms of other variable, then that has to be integrated first, right? So because the limits of V are in terms of u, first of all you will have to integrate over V so that the answer is in terms of u, and then you integrate over u to get a number. Okay, so you can see yourself that if I interchange these limits, there will be a problem, right? Because how do you integrate? You start from inside and then go out. So I'm not going to go into the computations, but note the order of integration and solve by computing the inside integral over V first. You get an answer in terms of u and then you integrate over u. Okay. So as I said, this is a cooked up question in the case of if you don't do this change of variable. The change of variable is actually making your life complicated. It would have been easier to compute double integral over d of this directly. I would not use change of variable. But I just wanted to illustrate what happens when you do change of variables. Let us look at another example. So let D be the region bounded by x plus y equal to 1, x equal to 0, y equal to 0, and let u be x minus y, v be x plus y. Find the region D star in the UV plane corresponding to D. Use the variables uv to integrate this double integral. Now change of variable is actually going to make our life simple because we don't know how to integrate this. It's a complicated expression. So let us see what's going on here. So the region D is bounded between these three, right? X equal to 0 is the y axis, y equal to 0 is the x axis, x plus y equal to 1 is this. So this shaded region is the region that we are talking about, right? It's a type 1 region, it is a type 2 region, those things can also be there, but still integration would be difficult. What happens to this region when you make this change of variable? So what happens is this triangle goes to another triangle. So what is y equal to 0? Y equal to 0 is x-axis. Where does it go? So if y is 0, right? So let us see. Let me explain it to you in some other way. Okay. So here u and v are written in terms of x and y, but we want x and y in terms of u and v. So x is given by this and y is given by this. Okay, just simple manipulation. So if x is 0, then u is equal to minus v. So that is this line. So what happens is x equal to 0 is what? Y-axis. So y-axis goes to this line u equal to minus v, and x equal to 0 with, y equal to 0, which is the x-axis, goes to, so y is 0 goes to v equal to u line, this line. And when x plus y equal to 1, which is this third line, goes to v equal to 1, right? Because v is equal to x plus y. So this is the triangle which you get when you transform this to this, xy to uv. So this is your D star. Okay. Now what are the limits for D star? It is not a type 1 region. You can check. It's a type 2 region where v goes from 0 to 1 and u goes from minus v to v. That's what I have written here. So take a pause, convince yourself that this is what is happening. So if you compute the Jacobian determinant, it comes out to be half. And if you look at the double integral, you replace the variables. So x minus y is u, x plus y is v. Multiply by the Jacobian determinant, which is half. So half comes out. V limit remains outside because it's constant, and u limits are inside because they are in terms of v. Cos u by v dv du. Right? Now this can be easily integrated. You first integrate with respect to u, and then you get a function of v, and then you integrate with respect to v. So I'll leave the computations to you. Finally, let us look at another example. So let D be the region inside the square with vertices, these 4 vertices. Evaluate this integral. So this is the region D. These are the 4 vertices. This is the region that one is talking about. Now one can use, you can break this into type 1 region, union of type 1 and type 2 region, and integrate directly. But a very simple method, change of variable, a very simple change of variables converts this region into a rectangle in UV plane. So now you have to be smart here as to what the new variables should be. So if you look at this line, this is x plus y equal to 0, and this line is x plus y equal to 6. So you see x plus y, right? So it's natural to take x plus y to be some variable, and this line is x minus y is 0, and this line is x minus y equal to 6. So it's natural to take another variable to be x minus y. So let us see. D is neither a type 1 or type 2 region. However, it can be expressed as a union of 2 type 1 regions by taking this, and it can be expressed as a union of 2 type 2 regions by breaking this like this. We will use suitable change of variables which will simplify the integration. So you take u to be x plus y and v to be x minus y. Then what happens to x plus y equal to 0? It goes to u equal to 0, which is v axis, and x plus y equal to 6 goes to v equal to 6. U equal to 6. Similarly, x minus y equal to 0 goes to v equal to 0, which is u axis, and x minus y equal to 6 goes to v equal to 6, which is this line. Okay. So D star becomes the square U0606 in the UV plane, and but when you convert into new coordinates, you want x and y as functions of u and v, so that you do. Then you compute the Jacobian determinant, it comes out to be negative half in this case. You compute the integral, x plus y is equal to u. multiply by absolute of Jacobian determinant, which in this case is absolute of minus half, which is half. Now u and v limits are both from 0 to 6. So you get this. So now I have done something here. I have split this integral into two integrals because both are constant limits, right? So you can think of integrating u over the limits of u and 1 over the limits of v. So that's what I have done here. So convince yourself that this and this are equal. Okay, because we are doing over rectangles and your function does not have any interrelationship between u and v. Okay, so let us stop here.